Have you ever been on a roller coaster, hanging upside down, and just wondered, how in the world am I not falling out? Well, today, we're going to crack that exact physics puzzle. We're diving deep into vertical circular motion and figuring out the secret code that keeps things in the loop. I mean, it's the classic question, right? You're at the very top of a loop, completely upside down, but you feel pinned to your seat. You might think it's some kind of magic, but nope, it's pure, awesome physics. And by the end of this, you're going to get it completely. So here's our game plan for today. We'll start with the challenge itself. Then we'll gear up with the right physics tools. After that, we find the secret, the critical speed. Then we'll put it to the test with a real problem and wrap up with a solid strategy to help you ace this on any exam. Let's do it. Okay, first up, the loop challenge. Before we can find any answers, we've got to really understand what's going on. We need to get a feel for the forces and the other variables that are changing every single second as an object moves in a vertical circle. You know, the biggest thing that makes this different from just spinning something around horizontally is gravity. Think about it. On the way up, gravity is fighting you. It's slowing you down. And on the way down, it's helping you out, speeding you up. So your speed is never, ever constant. And that's what makes this so interesting. The other huge player here is tension. That's the pulling force in the string, or if you're on a roller coaster, it's the normal force from the track pushing on you. At the very bottom of the loop, that string has to work overtime. It's holding the object's weight and yanking it into the circle. But at the top, gravity is actually helping out, pulling down, so the string gets a bit of a break. That change from max to min is absolutely key. All right, so how do we actually solve this? Well, it's time to open up our physics toolkit. And the good news is, we don't need 100 different formulas. We just need 2 really powerful, fundamental laws that work together like a dream. So here are our tools. On one hand, we've got the conservation of energy. Think of this as our energy accountant. It lets us track the object's speed as it moves from the bottom to the top and back again. On the other hand, we've got centripetal force. This is the law that's all about the circle itself. It tells us exactly how much net force we need to keep that object on its circular path. So one tracks the speed, the other tracks the forces. Okay, our toolkit is ready. This is it. This is the aha moment. We're about to combine these 2 amazing ideas to find the absolute bare minimum speed you need to just barely make it around the loop. This is the secret code we've been looking for. Let's zoom in on the most dangerous, most critical point. The very, very top. When the object is right up there, what's pulling it down toward the center? Well, 2 things. The tension in the string is pulling down, and of course, gravity is pulling down. Together, the sum of those 2 forces is the centripetal force. And that gives us our starting equation. T plus mg equals mv squared over r. So here's the real insight, the key that unlocks everything. What does minimum speed actually mean? It means you're going just fast enough that the string is about to go limp. It's the exact moment that the tension disappears. For just a split second, the string isn't pulling at all. It becomes 0. This is the same reason you feel weightless on a roller coaster drop. The track isn't pushing on you, so you feel like you're floating. And that idea, T equals 0, is everything. So if we take our equation and set tension to 0, what's left? Just gravity is providing all the centripetal force. We do a little bit of quick algebra and bam, there it is. The minimum speed you have to have at the top of the loop is the square root of g times r. Any slower than that, and you're not making it. That's the tipping point. Okay, so that's the speed at the top. But let's be real, you don't start the motion at the top, you give it a push from the bottom. So the real question is, how fast do you have to be going at the start, at the bottom, to make sure you're still moving at least the square root of gr when you get to the top? For that, we turn to our other tool. This is where conservation of energy is our best friend. It lets us connect the bottom and the top without worrying about all the messy changing forces in between. We just say the total energy at the bottom, which is all kinetic, has to equal the total energy at the top, which is a mix of kinetic and potential. All we have to do is pop in that minimum top speed we just found and then solve for the speed at the bottom. And after all that, here is our grand finale answer. The minimum speed you have to give an object at the very lowest point to complete a vertical circle is the square root of 5 times g times r. That's the number. That is the code for the loop-the-loop. Now, theory is cool and all, but let's make this really concrete. We're going to take our shiny new formula and put it into practice with a classic exam-style problem. This is where all that hard work really pays off. Okay, check this out. We've got a body with a mass of 1 kilogram, tied to a string that's 1 meter long, so that's our radius, and they tell us to use 10 for g. And the question asks for, you guessed it, the minimum speed at the lowest point. We literally just found the perfect tool for this exact job. So we don't need to start from scratch. We just grab our formula. V equals the square root of 5gr. Then we just plug in the numbers. G is 10, R is 1, so we get the square root of 5 times 10 times 1, which is the square root of 50. And to make it look clean, we simplify that to 5 root 2 meters per second. And that's it. We're done. So simple. All right, let's bring it all home. We have cracked the code. We've solved a problem. Now, how do we turn this knowledge into an actual exam-winning strategy? What's the ultimate payoff here? Here are your pro tips. First, if you can, always reach for conservation of energy. It's just easier math. But the biggest hack? Memorize these two critical speeds. Square root of gr for the top and square root of 5gr for the bottom. Seriously, having these in your back pocket will save you so much time on an exam. They are your ultimate shortcuts. And if you're trying to figure out what to study, focus your energy on these high-impact areas. You see how they're all connected? Vertical circular motion is the perfect problem because it pulls together energy, work, power, and forces all into one. If you can master this, you've pretty much mastered the whole chapter. And really, that's what this is all about. When you truly get the core concepts, like what energy conservation is really doing or how centripetal force works, a problem that looks super complex, like a roller coaster loop, just transforms. It becomes a simple, elegant puzzle that you know exactly how to solve. So there you have it. You've now got the tools, the formulas, and the strategy to handle any vertical circle problem they can throw at you. You have officially cracked the code of the loop. So keep asking questions, keep being curious, and I'll see you next time.